Hello everyone, welcome to Powertronics and Instrumentation class. In this video we are going to deal with two topics of the sixth module. The first one is the frequency synthesizer and the next one is the spectral analyzer. Now let's move to the first topic, that is the frequency synthesizer. Now what is a frequency synthesizer? It's actually giving you an AC output with a highly accurate frequency. So you have two types of frequency generators. That is, it's actually giving you sinusoidal output, right? Frequency generators are giving you sinusoidal output. You have free running type of frequency generator and you have synthesizers. Now the free running type of frequency generator, it's giving you an output that gives you a range of frequencies, and the frequency can be changed either mechanically or it can be changed electronically. Now their frequency is good, their accuracy, their overall performance is good, but you have poor frequency, poor accuracy and poor stability. So in order to overcome these particular drawbacks, synthesizers have been developed. Now the synthesizer is actually deriving your output. Right, your synthesizer deriving an output from a fixed frequency, and you have it's completely stable, and you get the output in a series of steps. So you can choose whichever frequency range that you desire. Now, frequency synthesizers are two types. You have direct type and indirect type. Now, in your direct synthesizer, you are having a crystal oscillator, and you're actually giving a set of multipliers and mixers. So what happens is that you're using these multipliers and mixers, and you can get your output in particular stages. Whichever desired frequency you want, you can get it. So here you are actually using multipliers and mixers. Now in your indirect synthesizer, here also you are having a crystal oscillator, but the difference is that you are actually using a phase locked loop concept over here, and your output will be a fraction of the particular input. So let's just see the block diagram of an indirect frequency synthesizer. Uh, right, indirect frequency synthesizer is given over here. Right, now you can see over here you have your reference frequency and you are giving it to a phase lock loop control. Now your phase detector, what it's going to do is that it's going to compare the reference frequency f1 and this is actually frequency f2. The frequency coming over here, this one is actually f2. So you are actually comparing f1 and f2, and you are checking whether it is equal or not. Now f2 is the frequency that is actually the present particular frequency, and you are actually pushing f2 towards f1. So the control is being done such that f2 will be equal to f1, and actually this arrow is coming like this, right? Okay, so it's actually a feedback. Right, so it's given to the phase detector, and filtration is taking place, it's being amplified, and then it's sent to the voltage control oscillator. Now you can see over here the particular frequency is being set into the voltage control oscillator, and then it's being sent over here. Right, so this is the basic concept of an indirect frequency synthesizer. You are actually using the phase lock loop control. So once the frequency becomes same, your system gets locked, and it continues in this particular manner, in the same particular manner. And if you're going on to the direct frequency synthesizer, you can see over here you have the crystal oscillator, and your crystal oscillator is sent to a set of mixers and filtering devices, and you can take your output from any particular stage. Right, so here you can see if you're turning the knob, if you turn this particular knob, you can set whichever frequency that you need, and correspondingly you will be getting the changes in the output. So here in the direct frequency synthesizer, you are using a set of multipliers and mixers to get the required output. So that was your frequency synthesizer. Next, moving on to the spectrum analyzer. Now your spectrum analyzer is actually a device which helps you to study the energy distribution of a particular signal across the frequency spectrum. Right, so usually we are viewing all the signals in the time domain. Now here you can actually study the energy distribution in the frequency domain. Right, so that is what your spectrum analyzer is doing. Now it gives you information about the bandwidth and different types of modulations, etc. We can go through what are the applications. Now, usually you have two types. You have an audio frequency analysis and radio frequency analysis. Usually we use the RF spectrum analysis because most of the communication, navigation, radar, etc., all of these are taking place in the radio frequency range. So we usually use the RF analysis, and right, you can portray the amplitude of particular signals in as a function of frequency. Now, you might be aware that if you're taking a particular sine wave, you have sine omega t. You can see that this is actually with respect to time. So here what we're going to do is that instead of omega t, you are actually, I'm just saying it as an example. Okay, instead of omega t, it will be converted into a function of frequency. Here sine is actually a function of time, right? Sine omega t, where t is the variable over here. Now, what you're going to do is that basically you're going to convert your signal into a frequency domain, and then you're going to do the analysis, right? So you can just see the basic block diagram over here. We are actually setting the frequency by using a sawtooth generator, and the sawtooth generator is giving you the ramp voltage, which gives you the particular frequency. And this sawtooth generator, the ramp pulses from the sawtooth generator, it is given to the local oscillator, which is given to a particular mixer. And this particular sawtooth input is also given to the horizontal plates of the CRO. Right, so the frequency is being set on the horizontal plate of the CRO, and you are giving your radio frequency input to the mixer, where the mixing is taking place with respect to the input as well as the frequency signals obtained from the local oscillator, and this will give you an intermediate frequency. Intermediate frequency is called IF. Right, so you are getting an intermediate frequency, and this intermediate frequency is being amplified, it's detected, and it is provided to the vertical plates of the CRO. Right, so your vertical plates are giving you the amplitude or the magnitude of the particular waveform, and you can see over here it is plotted against frequency. So basically what is your CRO doing? Your CRO is actually giving you a display. You can find out the display of any of the signals with respect to time, right? Usually it's with respect to time. Now here what we are doing basically is that we are converting it into terms of frequency, right? So basically what you're going to do over here is that you're using it to find out the frequency components which are displayed along the x-axis of the CRO. Right, so this has been already been discussed. You are getting a plot of amplitude versus frequency. You have amplitude versus frequency over here. Right, so that is what your CRO is going to be plotting, and these are the spectra of different signals. Right, so you have the continuous wave signal, amplitude modulated signals, frequency modulation, and pulse modulations. Right, now your continuous wave signal, it's actually simple, basic. You can think of it as a basic sine wave. Now your sine wave, you can see that in your sine wave, if you are checking your normal sine wave, it is having only one frequency. Right, since it's having only one frequency, what's going to happen is that your display will give you just a single spike. That is, this spike is representing, right, this spike is actually representing the that the output is present only at a particular frequency. Only at one particular frequency you have an output, and that is given as a single spike. Now if you take the case of amplitude modulation, what is amplitude modulation? You are giving a carrier wave, you are giving a reference wave, and then finally if you have two signals like this, okay, my drawing is not quite good. What will be your amplitude modulated output? It's going to be somewhat like this, right? Right, again I apologize, my drawing is not good. Right, so this is your amplitude modulated wave. So here you can see that there are actually three frequencies. You have a particular frequency, that is this particular frequency, right, the low frequency wave. Then you have the this is the high frequency. Okay, this is the high frequency signal. That frequency is present in this wave, right? That is constant throughout. And then you have a frequency like this. That is, I can say Fc plus Fs. And you have another frequency that is Fc minus Fs. So basically you have three particular frequencies present in one particular signal, and this is displayed in the particular as the particular output of your particular amplitude modulated spectra. Right, so in your amplitude modulated spectra, you have a particular frequency Fs, and then you have two sideband frequencies, that is Fc plus Fs and Fc minus Fs. So this is what is your spectra going to look like for an amplitude modulated signal. What about frequency modulation? Now, if you are aware with about frequency modulation, again over here you have a low frequency signal and you have a high frequency signal. How is your output going to be? Okay, this is going to be very difficult to draw. It's going to be somewhat like this, right? This is your frequency modulated signal. Now, can you tell me how many different frequencies are there over here in this particular signal? It's quite difficult to say, right? You cannot actually pinpoint how many different frequencies are there, because each section is working on a different frequency range, and therefore the number of side bands which are present or the number of bands which are present in your frequency modulated spectra are going to be infinite, right? You're going to have infinite number of side bands for the frequency modulated spectra. Okay, here you can see that the frequency of this particular wave and this second wave over here, it's different. So we have n number of frequency ranges, and that's why the spectra will be having infinite number of sidebands. And finally, you have the pulse modulation. Now, in the case of pulse modulation, your output is actually going to be a rectangular waveform, but this is actually in your time domain. But if you convert it to the frequency domain, you can see that it can be broken down to individual frequency components, and you can get a certain number of sidebands present in the pulse modulation also. So these are the different spectra of some of the different signals. There are many different types of signals, right? And moving on to the applications, you can find out what kind of modulation has taken place on the particular signal. Like if it's just one pulse, that means there is no modulation, it's just a simple continuous wave. Suppose there are infinite number of pulses, so that means it is a frequency modulated signal, right? And you can study the harmonic components which are there in a particular signal. You know that the harmonics frequency ranges are varied, so you can study the harmonic components of a particular signal. Then you can check the purity of the signal. You can determine the modulation, intermodulation. If any intermodulation has taken place, it can be found out. Then you can measure the pulse width and the repetition rate, the frequency modulation, deviation, noise. All of these can be found out using the spectrum analysis. Now, the main drawbacks of spectrum analysis is that you cannot measure transient events, then relative phases cannot be found out, and the major drawback is that the measurement time is quite high. So, it's actually time consuming. But again, if you want to find out about different modulation signals, you can always use this particular analysis technique. Right, so that was the spectrum analysis, and we had also gone through frequency synthesizers. Now, in the next video, we'll be going through the logic state analyzer and the digital storage oscilloscope, or the DSO. So please stay tuned. Thank you.